Okay, let's see.
I would love like the right side of like if you're looking at the professor from the stairs from the seating, I would like
Uh,
bottom.
ooh, okay. So
But like that.
so today I'll finish the material for the second exam, which is next Wednesday. I think on Monday I'll probably just like lecture for like 30 minutes the most, and then like the rest I'll leave kind of like office hours, I think, like last time. So one, two, yes, sir. So just check the study guide I sent earlier today. I just have to update it because depending on how much you cover about on series today, I will, that's where like I will have it. But yeah, so my plan, as I was saying, like next Monday, yeah, I won't lecture that much so that at least you have like an hour or 50 minutes to ask me questions if you have any. And I will still do, and then on Monday, I can also tell you how many problems I'll have because I mean, like, I'm going kind of like for five, like last time, but like these, some of may have parts. So like, it's kind of like how you end up counting them. But I will still kind of do the same where I'll kind of put one copy paste from workshop slash examples done in class. And I'll also do the same for one of these like worksheets, like, like the coordinator send like a review sheet, like problems. I'll take one of those like without any changes and just drop it somewhere as one of the problems. So, I mean, I still kind of start first with the workshop problems and the examples we have done in class, because I will ask more like prioritize things that are similar to what we have done. But like that review is kind of like worth like looking into. Yeah. I mean, not, I mean, like the only thing that I will kind of like explicitly is from the first exam is like integration by parts, but only in the sense that maybe like some of the integrals here, like you need to use integration by parts in the process. I wouldn't have like a problem that's just like do integration by parts because that's kind of like already covered. So there won't be any workshop problems. Like I wouldn't take it from like the workshops for the first exam, only the brand new ones, if that makes sense. Yeah. Yeah, right. And maybe including the one tomorrow, right? Yeah. Oh, sorry, were you? I still haven't, I mean, again, I depends on how many parts I'm going for five, but some of may like, one problem could be like analyzing two series. So like 5 pages, like that's what I want to say. But like I can tell you after I write it on Monday. Well, for Monday. Oh, where are you going to ask? I mean, they are on Canvas. Yeah, yeah, yeah. Like, let me see if I can. I mean, let me see if I actually let me stop sharing here for a second. I think so. I mean, if not, I should like I may not have updated them. Um, I mean, I think if you go here, like I don't know if how many workshops we have done so far. I may not have like the most updated version, but I usually drop them there. Like, oh no, 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 you're good, no worries. Um, oh, and by the way, because L'Hopital's, as I said, for finding limits, that is a useful skill. So I kind of like just posted some old notes I had. Like, if anyone needs like a review from L'Hopital's rule, like you can just go through it, skim through it, like just to make sure like you like are aware with the examples that because like finding limits of sequences is not that different. What I was saying like last time, and that's why I'm not focusing too much on it. I said finding limits of sequences is not that different than how you would have found it in Calc 1, like for functions. So it's basically the same idea. Um, so sometimes squeeze theorem works, sometimes L'Hopital's rule work. So I think those are the most important two skills to have, like squeeze theorem and L'Hopital's. But since it's not that different from like the Calc 1 stuff, I won't ask too much about it. Though, kind of like to summarize, the reason we were talking last time about sequences is so that we could have like some useful terminology for series, which is really what we care about. So what I was just to kind of like refresh your memory on like what a series is. So the idea, a series is kind of like a way to try to an attempt to make an infinite sum. So given the notation that we wrote last time, like a series will look something like this. And so what that means is A1 plus A2 plus A3 plus A4 plus A5 plus A6 plus A7 dot 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 dot. Right. And the point, the key is that what is this dot 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 thing, right? So here A1, A2, A3, A4, like there are the elements of a sequence. So what can be confusing at first, and that is like the important thing with a series, is that there are two sequences. When you talk about a series, there are two sequences that you have to be aware of. So for a series, there are two sequences to be aware of. So sequence one is the sequence AN, which is like the sequence of numbers you're actually adding. So let me put this one first. So sequence one is AN. And so these consist of the numbers you're adding. So these are the numbers you're adding. And sequence two, like the second sequence that that occurs in a series is a sequence of partial sums. Because the idea, and that's kind of what I was mentioning last time, the way to think about a series is that you don't want to do the sum right away, because doing it right away would be infinitely many terms. You don't know how to add infinitely many terms. What you can do is kind of like truncate the series. So for example, you would add first the first three terms, right? That gives you a number. Then you would add the next four term, like the first four terms, that gives you another number. Then you add the first five terms, that gives you another number. Then you add the first six terms. So you see, like, you kind of add one term at a time. And so that gives you a sequence of sums, which are called partial sums, because it's not like the totality of elements you're adding. So the second sequence there, and then the series converges, which is like the name that we'll give if that limit of partial sums exists. So the second sequence is called the sequence of partial sums. So this, I'll call it Sn. So this is like the sum. First, let me put it like in terms of the symbol, but then I'll put it in words. So Sn is going to be the sum of the first n elements of the sequence. Of sequence one. So for example, let's do it here. Like, what is S1? S1 is just one. What is S2? Is A1 plus A2. What is S3? Let me go up a little bit. Okay. What is S3? Is A1 plus A2 plus A3. Okay. And you continue that way. And so Sn is going to be A1 plus A2 plus A3 up to AN. Is that making sense? So you see, like, that also gives you like a sequence. So there are two sequences in play. One is like of the summands of the series, if you want to think about it that way, like the numbers that you're actually adding, and then like the sums that you're getting like at one step at a time. So for example, just to make it more concrete, if if the sequence had been like AN equals 1/2 to the n, right? So A1 is 1/2, A2 is 1/4, right? Actually, let me write that horizontally because it would be easier. So uh, if you use this sequence, A1 is 1/2, A2 is 1/4, A3 is 1/8, right? Because they're like the different powers of two, like, so it's, and then A4 is 1/16, right? Et cetera, et cetera. But what would be the sequence of partial sums? The first sum is 1/2. The second sum is 1/2 plus 1/4. The third sum is 1/2 plus 1/4 plus 1/8. And the fourth sum, sorry, S4 would be 1/2 plus 1/4 plus 1/8 plus 1/16. And that continues. So you see, like, there are kind of like two sequences at play. Uh, Up or down? Oh, down. Okay, is that making sense? Any questions about this so far? So good. And so the idea is that you say that the series is the limit of the partial sums. That's actually what the series is. So just to get it to write it down. So that is the limit as n goes to infinity of the sequence of partial sums. So it's the limit of partial sums. And so this limit is called the series is called convergence if the limit exists. Oh, yes. Oh, also, yeah. I mean, right, like, good catch. I will continue to start them at one usually. So, it doesn't really matter. I mean, of course, like the number of like for the sum would be different, but yeah, like whether this like the sequence, like, it's totally fine if someone wants to index like the sequences by starting at 0. But yeah, I'll try to stick at one, so like anyone can remind me if like I made that mistake. Yes.
How is this sequence different than just the original series? Adding all the two.
Oh, the thing is, like, you cannot do the operation all at once because you cannot add infinitely many things all at once, right? So like the thing, I mean, it is supposed to be the same. It's just that in practice, you cannot execute as infinite sum, right? What you can do is like add 100 terms, then a million terms, then a trillion terms, then a trillion of a trillion, and then see if there's like a pattern where like those sums are actually converging or like approaching a particular number. If they're approaching a particular number, then you would say that the series converges. So actually you say that this converges. We say it converges. Sorry, just to go up, scroll this up. We say the series converges if that limit is finite, if this limit exists. Yeah.
Series converges when there's some within it, some kind of number.
Well, not every smaller sum because the sums are kind of growing in a sense because you're adding an extra term to them, right? But it's not kind of like it's not that first you're taking the sum of like the first three terms, like, first three terms, and then like the sum of the terms 10, 11, 12, like, it's always like, the kind of like the next sum. Actually, this is a good point. Let me write it this way, which is actually hopefully more convenient, like from this recursive definition. If you remember, I had mentioned like last time that with a sequence, you can either give it by like an explicit formula or in terms of like the previous step. So if you notice the sum, kind of like the idea to have in mind, or let me like, okay, so this is correct, but oops. what this is saying is that if you think about it in words, it makes sense because it's saying the sum of the first n terms is the same as the sum of the first n minus one terms plus an extra one, right? So what I'm saying is that the series converges if this sum of like adding more and more terms kind of like approaches a particular number, like a finite number. But it's not kind of like grabbing at random. Actually, there's like if you ever take real analysis, there's like a very cool result that, like, say, for example, if you're adding positive numbers and the series converges, then you can rearrange the sum in any order and you still get the same like value. Like, it doesn't really matter in which order you added them. Like, I mean, but here, like, it's always the first term, then the first and second terms, then the first and second, and then third terms, and so on. Like, it's kind of like arranged. That okay? Is that making sense? Questions about this? Okay, so I'll show you the first convergence series, which will be like this one we have been discussing of like one half, like the powers of one, like different powers of one half. So, and this is one of the most important series. It's actually related to the Sinus paradox series, so it has like a lot of historical significance. But it will be part of a larger class, which is called like a geometric series, but I'll do this one specifically first for one half, just to kind of like have some more concrete numbers. So let's try to find the value. Which again, if you write it in the dot, dot, dot notation is 1/2 plus 1/4 plus 1/16 plus 1/32. Oh, sorry, I skipped 1/8, right? So plus 1/8 plus 1/16 plus 1/32, etc., etc., etc. And I mean, there is kind of like a picture proof that this should be finite, because the picture proof is kind of to say, oh, let's grab like a segment of length 1, right? And then break it in half, then break the remainder in half, right? Then break the remainder of that segment in half, right? Then break the remainder of that segment in half, dot, 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 right? So like essentially these numbers, like, that is where like they come from, right? Like these numbers are just obtained by like bisecting the remaining segment that you get, right? And so, if all of these numbers are coming from like this segment, it cannot be the case. Like, if you're adding them, you would expect that you get back one, because kind of like they are coming from like, they eventually should like kind of like recover like the entire line. That's kind of like, oh, not line, but line segment. That's kind of like the idea behind it, but it's kind of nice to do like a proof, that this is like actually the case. Okay, is that making sense? So I'll give you, it's like a very clever proof actually. But how are we going to do it? We analyze the partial sums, okay? So proof, or like, oh, how to find this value. We analyze the partial sums. So again, the partial sums are just, they are the sums up to the entry n in that list, like the nth entry of the sequence, the original sequence. So in this case, like 1/2 to the k. So it's 1/2, again, 1/2 plus 1/4 plus 1/8. plus, oh, sorry, were you going to ask me something?
I was gonna say,
You could have started, right, like, if you start you mean like the K at 0? Or, I mean, it doesn't like, there's not much of a difference, because the only thing that I like about doing it this way is that, the reason why I prefer to do it, you know, with 1 instead of a 0, because that kind of like, then these numbers are in matching in terms of like, S1 is the sum of the first term, S2 is the sum of the first two terms, and it goes from 1 to 2, and then S3 goes from 1 to 3. Like, if you started at 0, S3 would go from A0 to A2. So there's kind of like like an annoying, like, for the counting, it's kind of like sounds a bit odd, but it really, most of these things, whether you start them at 0 or not, like, doesn't like affect much of like the argument, you see. Um, I'm sorry, and this would go from, is that okay? So far, so good. So that is what the partial sum is. Now I will notice something that is kind of a cool, and that's like kind of like the trick in this in determining the value for this proof, for this sum, which note, what I'll do is kind of like factor 1/2 from each of these terms. So like, just to make it more clear, I'll write 1/4 as 1/2 times 1/2. I'll write 1/8 as 1/2 times 1/4. Then I'll write 1/16 as 1/2 times 1/8. And then I'll write 1/2 to the n as 1/2 times 1/2 to the n minus 1. I must say, like, most of the times, you won't be expected to find the values of series. Basically, we're finding kind of like the values for certain series that you need to really kind of know, and all the others are found from these ones. Because finding the value of a series is like actually like a very clever thing. It is hard to find the value of a random series. Like, that is one of the hardest things you can do if you mean by that like the actual number, right? So this is like it's like a very clever argument, you'll see, but it's not something that you would expect anyone to kind of like come up with like on the spot, so it's more like, I'll tell you what the value is, I'll tell you the formula in the general case, and then many other of the other problems can be just found from this particular formula. But it's not some like finding the value of a series. It is one of the hardest things you can do. Like like it's kind of like similar to this combinatorics or probability discrete math problems, which is how they're called. Like, when they ask you, oh, in how many ways you can divide this like number of balls into this other, like, all these problems where like the variables are not changing continuously, sometimes are harder because you have to do the counting or something clever. The calculus facilitates if everything were continuous. Okay, so what I'll do, since everything has a 1/2 here, I'll rewrite this sum as 1/2 plus, I'll factor out this 1/2. Let's see if I'm doing the way I wanted to. Okay, so I'll kind of keep it this way, but I'll actually, I mean, it's not the one that I check my notes, like, I mean, like, it's kind of like a useful thing to have, but it's not the one that we need, but at least I will continue it, like, just to show you a little bit of how the experimentation would work here. So like, if you find this way, this would be 1/2 plus 1/2. And what is this? This would be like the sum of the first n minus one terms, right? Like this would have been Sn minus one. That okay? So far so good. Is that making sense? Uh, no, I actually. Oh, sorry. Yes. Oh, right. That's a good question because if I had factored the first one, right, then I would get kind of like the same 1/2, but then 1 plus 1/2, right? And it's just like this partial sum start at 1/2. I don't have the one. If I had started at 0, which is what you were saying, like, there would be like an extra one. But yes, like in this case, uh, I cannot do that. So like, that's why I did it this way. Now, actually, like, I will say, mention something. This is actually like an important trick, which I do want you to have. So I'll kind of use this as an excuse uh, to, to show you what the value would be. So I'll put like a big if because I still haven't said that. But if you already knew somehow that the limit exists, then this will give you the value of the limit. So that's kind of like important to notice. So, but of course, like we still don't know it, but like at least I will tell you that it will give you the value. So if you knew the limit, that limit of Sn exists and equals L, right? And I will have like a problem. Like actually, I was going to give you these types of problems tomorrow on the workshop, but now I'm using it as a good excuse because it's like a very important idea for finding limits. So if somehow you know from heaven like the limit exists, then you can find the value for the limit. Like because then you take limit on both sides as n goes to infinity. Then this equation, the previous equation because what could you do? Like you found that Sn is 1 plus 1/2 plus 1/2 of Sn minus 1, and then you would take limits on both sides of the equation. So limits are kind of like things like derivatives or like squaring an equation. Like if you can square both sides of an equation, you can multiply both sides of an equation by 3, you can take derivatives on both sides of an equation. If you know the limit exists, you can take limits on both sides of an equation, if that makes sense. So like you can take a limit here. Of course, like to take the limit, you like for this to find something useful, you do need to know like that the limit exists. But then like the left-hand side would be L. Right? Then what it would be the limit on the right side? It would be 1/2, and then 1/2 of what? Well, this limit should also be L because it is the same sum. It's just like one element less, but like in the limit, it doesn't matter because everything gets added in the limit. So this one would also give you L. Let me put that like in color because like that's kind of like the important thing. And then you can solve for L because if you solve for L, you would have that, L minus L over 2 is 1/2. So L over 2 is 1/2. And that will give you that L equals 1, which is actually the value for the limit, right? But this all is predicated on knowing that it actually exists, which I still haven't told you, but at least there are sequences like, sorry, like just to go up. There are sequences, I'll give you like an example tomorrow on the workshop where like, if you assume that the limit exists, then that's how you would find the value for that sequence. So it's like a very clever argument. Yes. Sorry, as n goes to infinity.
So
Yeah, sorry about that. Yeah. Okay, so this is like a very clever way to find limits. Oh yes, sorry, wait. Oh, this is completely useless if you didn't know that the limit doesn't I mean, if you're agnostic on whether there's a limit or not, like, it doesn't matter what like this, of course, you can take limits on both sides of the equation, but then you don't know if you can replace it by a finite number or like an infinite. And, if you have infinity, everything is lost, right? Like it doesn't say anything. So, well, I mean, so yes, it's only useful. That's why I put if in colors because it's like a big if you already knew that the limit exists, right? But the thing is like there are ways sometimes to prove that a limit should exist without knowing its value. But that's not something that we'll go into. But I will give you like a problem where it's like, but trust me, this sequence has a limit. Find the limit once you know that, and then you take limits on both sides. You'll do some problems like that on the workshop tomorrow because it's like a very useful skill. Actually, the problem is kind of clever. Like it's kind of like about the Babylonians had like a method to find square roots from a sequence, and it's kind of like approximation to the square root of a number, and it's kind of cool. So you'll see that you get like that the limit should be the square root if you assume that somehow the limit exists. There's also like this Newton's method if someone is into algorithms or things like that, where that is how you find the zeros of a function, which is like defined through a sequence. And I mean, there are many things. I mean, sequences are actually pretty useful. But yeah, like here's like a big if. I said I started doing it this way, so since I started this way, I might as well tell you this useful technique now because it is like a really clever thing to know how to use. But yeah, like now I will justify why the limit exists, right? So I haven't done that, but like I will now. Yes.
So n minus one equals 1/2 times L.
Oh, so the thing is like with limits, so first like, think of this as this is the limit of a sum, right? So the limit of a sum should be the sum of the limits, right? So that's why this 1/2 comes out. Then it's kind of like same with derivatives or integrals, right? Like a constant comes out of the limit. So you're just really asking me why is the limit of Sn minus 1 also L? But if you think about it, like what is the difference between Sn and Sn minus 1? That there's only one extra term that's being added, but in the limit, all the terms are being, that's the beauty of the series. It's like the sum of all. So it doesn't matter, like it's kind of like you're behind me by 1 unit, but we're both moving towards infinity. So you see, like there's no element that's missed in the limit. Everything has been added by this one, if you know what I mean. Because what is Sn as n goes to infinity? It's A1 plus A2 plus A3 plus A4 plus A5 plus A6. This is exactly the same. It's just that it's one element behind Sn in the sum, right? Because Sn minus 1 is just one fewer element.
But as it approaches infinity.
See, everything gets covered. Right, exactly, because everything got covered, you see, because every element eventually gets hit by S. So it's kind of like imagine two moving cars. And yes, one is always behind, but in the limit, like they all went through the same points. Do you see what I mean? Kind of, yeah.
It's not really that intuitive, but.
It is,
makes sense.
but it's kind of like, I mean, it's kind of like an idea, right, because it's kind of involving infinity, right? But you do have to imagine like that's why I'm trying to use it with the analogy of moving. Like if you had two cars, like, one driving at 1 mile per hour and the other driving at 2 miles per hour east. Like imagine they're traveling along a line. One is 2 miles and per hour, the other 1 mile per hour. They travel for the eternity of the universe. I'm claiming that they travel the same because there's no point that eventually all the points would get hit by one of those, by the cars. And so it's kind of like the same that's happening here. It's true that this one is kind of like always one element below this one, but that element kind of gets always absorbed eventually as you increase the n. So there's no element that's missing in the sum, you see.
Because that element is always gonna
Absolutely.
cover the point that has sub n.
Right, yeah. Yeah, no, it is like, no, so they're like kind of subtle things with sequences and series, like to think about, but so you have to think about it more like as an animation moving towards infinity, and I do think that helps a little bit to kind of get a better picture of what's going on. But yeah, like actually, let me write it as a useful like idea. Like, so what I'm using is like this idea. So the idea is that if you have a sequence like Sn and a limit of Sn equals L, then a limit of Sn minus 1 would be L for the same reasons, like for example, like,
So if you do know the limit existed, you would still get a value, but it would mean nothing.
no, if you don't know that the limit exists, then the problem is that when you take limits on both sides of the equation, you don't know if you can replace that by L, because if L stands for infinity, like working with infinity, here I had to subtract these two things, right?
Yeah.
You cannot subtract infinity minus infinity, you see? So it's completely ambiguous. Like it's only if it's a finite number that is not ambiguous. That's why you do need to know that it exists. Now, yeah, let me just show you like, right, like, so you can actually do the calculation explicitly. So why does this exist? No, sorry, just to copy paste like that, the partial sum. So actually, like the thing is, like I factor out, and in this case, it was more useful to just multiply by 1/2. So let's put it here. So if you take this partial sum and you multiply both sides by 1/2, which is kind of like the rescaling, every term differs from the previous one by 1/2. That's kind of like the idea. So what would be 1/2 of S sub n? So everything is multiplied by 1/2. So this becomes like 1/4 plus 1/8 plus 1/16 plus 1/32 plus 1/2 to the n plus 1. Right? Every term got multiplied by 1/2. So like let me kind of like put the arrows to show you what they became. Is that okay? Is that making sense? And then the magic trick, right, is that kind of like you see there's a lot of overlap between the elements here, right, in both equations. Like the 1/4 are the same, the 1/8 are the same, the 1/32 are the same, The only thing that they're not the only thing 1/2 is not present in the previous one, and 1/2 to the n plus 1 is not present in the previous one. So if you subtract these two equations, the only thing that remains is the first element and the last element of the first element from the first equation and the last element from the second equation. So what I'm trying to say is that Sn minus 1/2 of Sn, you know, like that would give you 1/2 minus 1/2 to the Sn plus 1. Right, like because there's a bunch of cancellations, that's what I'm trying to say, like the rest canceled out. And then the left-hand side is just Sn/2, right? This is 1/. Then multiply both sides by 2, so you get Sn equals 1 minus 1/2 to the n. And here, like, it is more clear what the limit is, right, as n goes to infinity, because like 1/2 to the n goes to 0. So you see, it's not that different from kind of what we were doing before, but like in the previous argument, but here like you do have like an explicit formula for the partial sums, and so that's why it does allow you just to take the limit. Questions? Does that make sense? And okay, and as I was saying, this is a special case of a specific type of series called like geometric series. Okay, so this is a special case of a but the formula is found in a similar way. So I'll just give you what the answer is. This is a special case geometric series. Which is a series where you're adding powers of a fixed number. So, which is what we were doing here. We were adding powers of 1/2, right? Here, R is some number. So in our example, R was 1/2. Oh, sorry, yes. Oh, yes, yes. Let me see if I can zoom out a little bit as well. Is that good or? Oh, yes, before like I write the formula, yes. Yeah, essentially, yes. Right. You will get something similar to here. You would basically you would get kind of like you would get like kind of like an like I guess like the formula is more like here you kind of see like there's an R and then like R to the n plus 1 or something like that. So you need like the R to be less than 1 to converge. In absolute value, it could be negative, that's fine. And so you need R in absolute value to be less than 1. But that's essentially, but you can kind of like say it from here, right? Because you will get something like 1/. Like instead of one to over two to the n, you get something like r to the n, and you need that to go to zero, right, for like the limit to exist. So yes, that's a good catch. So right, like that's actually what I was going to write, that this is convergent. So the idea is that this converges. And you can, this is like the most classic series. So like the book has like the argument is essentially the one that I did, but you just multiply by r instead of 1/2 every side of the equation, and that's it. Uh, provided r is between, let's write it like provided r is between -1 and 1. And the value of convergence is r over 1 minus r, the value of convergence. And so this is one of like the most important formulas, like, you do need to memorize this one for the exam.
So if R is less than, so if R is zero, the value is one.
Well, no, the thing is, well, I mean, it's kind of like this annoying thing of like, right. I mean, powers of zero, yes, are zeros, right. So that's, right, like, and this is covered. Yes, like it does work for r equals zero, right? Because if you put r equals zero here, like the numerator is zero. So actually, that's like what you would call like a sanity check, because like the formula does work at zero, which is great. So, and then if you, for example, try to take r equals 1, right? It's 1 plus 1 plus 1 plus 1 plus 1, and this should be 1 over 0, which should be infinity. So that also makes sense, you see.
So, and then also if R is less than zero, like the first term will be adding, and then it'll be subtracting, and then adding. And
Right, it's kind of like a flip. Right. It's plus minus plus minus plus minus. Yes.
So like the value would be less than if that R was the same magnitude of the R.
Ooh, correct, right. Yes, that's why it kind of continues working. The idea, I mean, we will talk about that more like when we talk. There's something called like absolute convergence versus which means like the sequence in absolute. If you take the absolute value of every element, that it converges, and so when that happens, like then without absolute values, it's supposed to converge, because like the idea is like kind of like when you have positives and minuses, it's easier for like the sum to become finite. Because the worst thing you can do is add all positive, right? If you add all positive, they all contribute to one another. When you have positive and minus, they're kind of cancellations. So in a sense, it's easier to get something finite if you're allowed to have cancellations as opposed to something just positive, right? Because if it's just positive, then that thing will keep growing. When this plus minus, there's like a better chance of convergence, because then the minuses kind of help cancel out a little bit of like the positive stuff. You know what I mean? But we'll talk that. I mean, that's like a more important, like that is like a topic we'll talk about like after after spring break, I guess, because like the exam is the last day before spring break. So, but that's like an important idea as well. Is that okay? Is that making sense? Questions about this? Um, okay. So this is like a very important formula. Here's another important thing that I need to tell you. So it's always nice to kind of like start with like a series where like, like this is like the most classic series ever. Like, here's another important formula. So I already had mentioned this, right? But now I'm going to turn it around. And I had said before, I'll write it here on the board. I had said before, right, that the sum of the first n terms is the sum of the first n minus 1 term plus the nth term of the sequence, right? So you can do something which seems kind of silly, but that if you kind of subtract this sum, that gives you like a formula for the nth term of a sequence. It's like the difference of the two consecutive partial sums, right? So, right? That makes sense, hopefully. And you would say, okay, why is that useful? Because if, right, if the sums converge, right, if the series converges, right, now we actually, this trick that I did earlier at the end was kind of useful that I did it because now I'll apply it here. So if the series converges, in the sense that, so the limit as n goes to infinity is a finite number, right? Is some number. Then what happens here? You know, let's do exactly what I did before. Take limit on both sides of the equation. Right? And so what do you get here? You get that the limit as n goes to infinity of a sub n, right? What is this? It's L minus L, right? Because of what we were saying before, like that partial sums both have the same limit, right? So you get L minus L, which is 0, right? So that means that, uh, so So that means that if you know, sorry, just to, I'll kind of write it in a word, in a way that's a little more convenient in practice. What this is saying is that if you know that the series converges, then that means that the nth term of the sum had to be going to 0. The way that it's actually useful is kind of like in the reverse version, which is called the contrapositive. If you like kind of like ever studied like logic. So what this says is that if the limit of the sequence of summas is not 0, then the series cannot converge. And that is like a very useful criteria. And so that's called the nth term test. Let me write it down. So it says that if the limit as n goes to infinity of a sub n is not 0 or does not exist, either is fine. Then the series cannot converge. So meaning that it diverges. Yes.
Is that enough to say that series does converge, or is it just necessary?
Right. So what I'm saying is, okay. So it depends on which version of the statement. A necessary like I don't want to use that language because not everyone may be familiar, but like a necessary condition for the convergence of the series is that an term goes to 0. It's not sufficient because there are series. I'll kind of give an example of each, right? There are series that whose end term goes to 0, but still they don't converge, right? So like right, it's like there's difference between like necessary and sufficient conditions, right? Yes. So in fact, like the harmonic series, that's a good excuse to mention the harmonic series, which I will in a second. But the harmonic series does not converge. So but let me write it like but just at an intuitive level, what this is saying is that if you want the sum to be finite, you have to be adding smaller and smaller things. That's kind of what it's trying to say, like this statement, which kind of makes sense. Like like how can the sum be finite if you keep adding things that don't go to 0? Like that's what it's supposed to say. So let me give you an example to clarify this. This like the necessary versus sufficient condition. So let's say you were trying to determine whether this series converges or not. Sorry, this should have been a king. Okay, so I don't know, should this be finite, should this be infinite? So what I'm saying is that let's call a sub n the element, the nth term of that sequence. So call of that series. Oh, sorry, this should have been n. Right, so these are the elements that you're adding like in the series. What is the limit as n goes to infinity of this quantity? So I would do something that you would, sorry. Oh, but plus n, you mean? Yes, thank you. Yeah, thank you. Yeah, good catch. So I'll do something that you can call kind of like order of magnitude analysis, which is in the limit, right? In the limit, because we're going to the limit, n plus one is more or less indistinguishable from n. There's no difference of adding one to 1 trillion, a trillionth of a trillion, like, So when you compute the limit for all practical purposes, again, like if you wanted, you can just like think, oh, let me just replace n with n plus one. There won't be any difference like in the value at infinity. Same goes here. In the limit, n squared is significantly faster than n. Like if you were to compute the growth rates, like the square goes way faster towards infinity than n. So in the limit, this is actually kind of like an epsilon, like a nothing, like, it's a fleet, like nothing counts. So like you replace this with 4n squared, right? And now this is super easy to simplify because you can take the 4n squared from the square root, right? This can all be justified with L'Hopital's theorem, if you want it to be super strict. But if you do it this way, I'm fine with it because it's kind of like understanding the growth rates, right? So like the idea is like a quadratic thing grows way faster to infinity than a linear thing. So and this gives you one half. And so what that means is that at the end of the day, basically all these numbers that you're adding are like one half, one half, one half, more or less. And so that cannot be finite like some. What were you going to ask him? Yeah, you can do L'Hopital if you want, or like just do it kind of like this way, which like the more like you could also have factorial like an n squared, right? Like as long as it's correct, that's fine with me. But if you think about what does this mean? It means that in the limit, all the numbers you're adding are more or less like one half, right? And so that cannot, like the series itself is the sum of all those numbers, so it cannot converge because you're basically adding one half plus one half plus one half plus one half plus one half. So that is what the nth term says, that unless this number is zero, there's no chance for the series to converge. Okay. So this is not zero. By the nth term, n test. So I'll put that on the study guide, but I do want you to say like the magic words by the nth test. So it's kind of like the summoning of the, summon the theorem, just say by the nth test, like, this does not converge. Like, it's kind of like, like the witchcraft of like the problem, like, the summoning. So like, you just have to mention the theorem, like, Does that make sense? Like any questions about this problem? So again, this is what this task says is that whenever the limit of the sequence that you're adding is not zero, then the series diverges. But that doesn't say that if the limit of the sequence is zero, then the series converges, right? So I'll give you let me clarify this now, and I'll do it with the harmonic series. So remark, it is still possible. It's still possible for the limit of a sub n to be zero, and yet the series diverges. Okay, so that is totally allowed. So it's important not to confuse the two concepts. Yes.
Explain again why, uh, the limit as a partial sum goes to infinity means that like, it's the same thing as just paying that limit like a bunch of times in the series.
No, I think you mean I think what I was saying is that when we were comparing Sn minus here, oh, we had Sn and Sn minus one, right? What I was saying is that these two would have the same limit at infinity.
Yeah.
Because what does this mean? Like this means add the first n terms. This means add the first n minus one terms. You know, keep numerical parallels to this. So if n is a million, this will be add the first 909, like like nine, and then like, well, no, this would be the first million, and then there's like the 900,000, 900, you know what I mean? Like, and so, but then if it's a trillion, like what I'm trying to say is that you're always ahead of the other one by one element, but that element kind of keeps being reabsorbed into the smaller one, right? Because it's both are sweeping out the same, if you think of the sequence that you're adding kind of like as balls, you're kind of like along the line that you drop on the line, you both eventually go through all the balls, like, because you're going to see.
Yeah, that makes sense. But like, why? So the limit equals a half, right?
Right.
So,
I now see what you're saying. This is saying that the things that you were adding, right? This is saying that the things that you are adding in the limit, this is really close to one half. So the things that you're adding here are like one half. So you're doing one half plus one half plus one in the limit. Like, maybe after a trillion terms, this is already really close to one half. So it's kind of like doing one half plus one half plus one half plus one half. There's no way for that to kind of converge because you just keep adding one half.
so, since that sum notation, like the first one is almost like, so it's like two limit statements in one, almost. Like, it's the limit of the partial sum and then like the limit of that having goes to infinity.
I mean, well, right. This is always like right. Like that's why I was saying there are two sequences in this every series problem. One is the series itself, which is a limit of partial sums, right? And then the other sequence that is around is kind of like the sum, the terms that you're adding, right? What I'm saying is that because the terms that you're adding have limit one half, then the terms that you're adding are closer and closer to one half. So the sums themselves are adding a bunch of one halves. Yeah. So like that, let me finish with this. I do want to kind of like wrap today's, so like I do want to wrap up today's class by doing like an example of like the divergence. So what I'm saying is that you can still have the limit to be zero and yet the sequence diverges. So again, another classic example is this harmonic series, which I think it was like one of the Bernoullis who proved first that it is infinite. So and it is like a very cute proof. It just takes a picture to do. So okay. So notice that in this case, like this is like each term that you're adding is going to zero, right? So notice here. Okay, so so here in this series, we're adding things that are getting closer and closer to zero. Is that making sense? So the things that we're adding are becoming really small, but the point is that it's not going to become small sufficiently fast. That's kind of like the idea. We don't become small fast enough, and that's why this sum still will become infinite. Okay. So let me show you a proof of the idea, and then I'll finish by writing the last thing on the exam, which would be like this integral test. But you'll see where it comes from. So take like 1/x. Can you see what I'm doing? So I have like the graph of 1/x. I'm kind of like breaking the interval into like sub-intervals of length 1, right? And then I use the top, like I make a rectangle where like top left corner like is on the graph of the function, right? So what is the area? What is the area of the first rectangle? The first rectangle has area 1. What is the area of the second rectangle? 1/2, right? What is the area of the fourth rectangle? 1/3, right? Is that making sense? So hopefully this convinces you. And notice that this is always a little bit more than the area under the curve. There's like an extra stuff. So this should convince you that the integral from 1 to n of the x over x is less or equal than the sum of the first n terms of the partial sum. Right? Is that making sense? So here, like I said, 2. Yeah, that's fine. Oh, well, I guess n plus 1 because this goes like yeah, if it's from 1 to 2, then it would just be 1. So that's fine. And let's put n plus 1 here. Actually, because there's a shift. But we do know at n goes to infinity, this diverges, right? This is a p series, right? Like this divergence because p equals 1. Okay, so what does that tell you? I mean, this is like what you would call like a lower bound. This is always below, this partial sum. So that kind of like drags like the partial sums to infinity. So that forces. So this is a bit better than just saying that the series does not have a limit, because it is, I mean, in a sense, it is a limit, but it's just like an infinite limit, like it's just like, it's saying that if the sum does increase without any bound, you can always add more terms so that it's kind of more than 100 or more than 2,000 or more than 3,000, etc. Okay? Is that making sense? And essentially, there's like a thing called like, and that's like the last thing I'll write. There's a thing called the comparison test, which says that there's series that you can compare with an integral, and they kind of have both the same fate. Like they're either both finite or both infinite. Like so, like let me write that down, and that will be like the last thing that I'll do for that will be on the exam. So like the comparison test is essentially kind of like this picture. It's kind of like you have a function. Actually, let me draw it like this. So you have like a positive continuous function. Continuous function, which is decreasing, as you can see in this picture. And here's A1, A2, A3, A4, A5, okay? And so it has a property that f of n is an. So here's 1, 2, 3, 4, 5, etc. So what the comparison test, like the thing is that you can rearrange the rectangles kind of like in this picture. Sorry, in this picture, I kind of chose like the corner so that the area would be higher of the rectangles. But if I had used like the lower, like the other vertex, like then the area would have been lower. So you can always kind of like sandwich things between like the two like series. So what the comparison, and I'll probably do like an example of this like next time, but like this would be the last thing that I include like this on the exam. And the workshop tomorrow will have some problems about it. But the idea is that in this under these conditions, these two integrals like have the same behavior. Sorry, the integral and the series either both converge or both diverge. It's like so they have the same kind of like destiny, like either both converge. That's why the terminology for improper integrals is essentially the same as that of series, like convergence, divergence, because like an improper integral is closely related to a series. Okay. Oh, sorry about that. And again, this will be the last topic. So I'll add it to this. I'll add this series stuff to the study guide, and then tomorrow you'll have some problems about this, and then I think I'll do 1 or 2 examples in class tomorrow on Monday, and then I'll kind of like switch to office hours type thing. Like, so if you have any questions, yeah, feel free to ask me that on Monday. Yes, like. Oh yeah, sure. Um, like here. Oh, to the geometric series, you mean? Oh, yeah, got you. Yeah. That part. Let me stop the recording. Oh, sorry, I